Thank you very much. Thank you much for the organizers for inviting me to speak. And this is a great opportunity for me and a great honor. My title is On the Number of Nodal Domains of Toral Eigenfunctions. I'm going to speak about eigenfunctions of the Laplace operator on the torus. And I'm going to formulate a result on it. To be able to formulate my results, I'll use inherently some theory of random fields, and I'm quite aware that this is an analysis seminar, and maybe not everybody is an expert. So I'm going to try to avoid mentioning random fields as much as possible, but at some point it's going to be inevitable. But nevertheless, I'll try to make it self-contained. So first part is background and motivation. So my talk is going to consist of 3 parts. First part, background motivation. Second part, I'm going to formulate the problem I'm going to try to solve and the results that are known. And third part is I'm going to formulate the results. So let me start from the general background. Let M G be a smooth, compact Riemannian manifold. Of n dimensions. And from this point on, I'm going to assume that n is going to be equal to 2. So this is going to be a surface or a billiard. Depending on whether or not it has a boundary or its boundary is empty. And I'm going to use the letter n for some different things, so it's never going to denote the dimension of the manifold. And I'm interested in the spectrum of the Laplacian. So this is Laplace-Beltrami more generally. At some point, I'm going to pass to the case when M is just the standard torus, so it's all just Laplacian on the plane. And in this general setup, I'm interested in the spectrum. So numbers lambda and functions f that satisfy this equality. And by adding lambda f to the left-hand side rather than subtracting it, all the numbers lambda are becoming non-negative. And in this general setup, we have the following spectral theory. So the spectrum is purely discrete. In case that there is a boundary, then we assume we make either the Dirichlet or Neumann boundary conditions. That's the condition that we impose. And then the spectrum is discrete. Lambda j are the energy levels. And we order them by non-decreasing order. And the corresponding eigenfunctions we denote phi naught, which is just the constant function, phi1, etc. Why do I write less than equal then and not strictly less? Because they may happen to have some spectral degeneracies, but usually depending on the geometry of the manifold, they're quite unlikely, except that in our case, actually, since we are going to speak on the torus, there are a lot of degeneracies. So I do write small equal then. And then the phi j constitute an L2 orthonormal basis of L2 of M. There is some ambiguity of choice of phi j in case that there are spectral degeneracies, but I'm going to ignore it altogether. and at some point when we're going to speak about the torus, I'm going to use a specifically chosen orthonormal basis. Now, the center of our, before that, we have Y law that is prescribes the number of energy levels. Now, I already said that the number of energy levels is infinite, but if we reformulate the question of how many energy levels there are up to some large number lambda, then this number is asymptotic to some universal number times the area of M times lambda as lambda goes to infinity. And we're interested in the nodal set. So definition. If f is a smooth function, then the nodal set, or the nodal line, in this case, because this is just a two-dimensional setup, is just the zero set of f. And we're interested in the nodal sets of phi j as j grows to infinity. Okay, and the question is, how do we describe it? Okay, definition number 2, we already know what is a nodal set. What is the nodal components? So these are the connected components of the nodal set. And I'm going, in a few seconds, few moments, I'm going to draw a picture, then everything is going to become clear. Well, I'm writing phi j, but in fact, it could be any function f. We're interested on phi j. And 3, what are the nodal domains? So these are the connected components of the complement of the nodal line. Okay, so I hope that it's not going to be anything creepy. So this is M. Suppose that this is the zero set of M. Okay, so suppose that our function is positive here, and negative here, and negative here, and negative here. Then we have 3 3 nodal components. This is 1, 2, and 3. And 4 nodal domains. This is the big one is 1. This is 2. This is 3. And this is 4. There are 2 types of nodal domains. There are positive ones, and there are negative ones. There's only one type of nodal component. It always connects between a positive and a negative nodal domain, at least generically. So, fact, generically, nodal set is a smooth curve. I'm not going to say in what sense it's generically true, but I could if anyone is interested. Okay, so these are the most basic object of our study. And the most basic quantitative question that we can ask is how many nodal components and how many nodal domains there are as j goes to infinity. So most basic. We denote it n of phi j. This is the number of nodal components of f of phi j. And we could also ask what is the number of nodal domains of phi j. And these two numbers are equal up to some Euler characteristic, which is O of 1. And from this point on, I'm going to ignore the difference between those two.
You also ask about the length of the
yes, you could ask that. But in fact, this is the more interesting quantity, in my opinion. Why it is more interesting, it's less known. It's less known. In fact, that's the next thing I was about to say. So this question of nodal components or nodal domains is non-local. In what sense? Suppose that I have this picture. Okay, what does it mean that something is local? Suppose that I would like to measure the total nodal length. Okay, then I can tile this manifold into small patches. I can compute the nodal length in each one of them, sum them up, and I get my result. However, if I would like to count the number, which is 3 here, of nodal components, if I tile it to patches, then, OK, there are two options to how do we count components inside a small patch. Either we count those that intersect, and then we count one here, one here, one here, one here, one here, etc. And when we are clearly severely overcount, or we count all those that lie inside this small tile. And in this case, we just sum up 0, and we end up with 0. So therefore, whatever way we choose, we're getting a wrong result for the total number of nodal components. And the conclusion is that this is a more difficult quantity to count than the nodal length, because nodal length is local, and the number of nodal components is non-local. But in fact, it was discovered quite recently by Nazarov-Sodin that this is some intermediate between local and non-local, which is called semi-local. Yes. But so in some generic situation that I'm not going to say now, what it means is that there are very few small nodal domains, or nodal components. Most of them are contained in the box of radius, say 1,000 or 100 over square root of the eigenvalue. Not individual, yes, but OK. OK, then cancel the previous paragraph. Yes, but OK, cancel the previous paragraph. Right. Now, what is known about n of phi j? So current nodal theorem, n of phi j is smaller or equal than j. The number of nodal components of an eigenfunction with index j, small equal than j, no matter how we choose the orthonormal basis phi j. If this inequality happens to be satisfied as an equality, then this phi j is called courant sharp. But there are only finitely many courant sharp for each domain, as the following statement holds. So Pleyel lim sup n of phi j divided by j. So this number divided by this number is more equal than 1 always. and this is smaller or equal than 0.691, strictly smaller than 1. Therefore, there may be only finitely many indexes j that satisfy this with an equality. And in fact, this constant, which happens to be some kind of zero of some Bessel function, some first zero of the Bessel function, or some kind of derived quantity, and this a number of on the right-hand side was improved recently by Bourgain in 2013 by 3 times 10 to minus 9, a small epsilon. Sorry? It's something like that. So this is positive number.
Is that? No, minus.
3 times 10 to the power minus 9. But the importance of this result is the technique and the fact that this number is, sorry?
You subtract that little number
Yeah.
from it.
Yes.
No.
No.
You don't multiply.
No.
That would be really.
No, absolutely not. Now, to the other end, there is no so there is no non-trivial. I don't think. Okay. No worries. I was mentally prepared for that. So no non-trivial lower bound other than n of phi j is greater or equal than 2. It's possible to construct an eigenfunction of arbitrarily high energy with just 2 nodal domains, even for the torus or the square. Okay, now any questions so far? So far, so good.
So is this final bound, is there something similar in 3 dimensions too, or?
Yes. So basically, both of them are holding for any dimensions. So there's no non-trivial lower bound, but perhaps in some generic situation there is lower bound if, for example, we restrict to a density 1 sequence of J or so. So whatever results I'm going to present in the third section, so as an immediate corollary from them, we will be able to disuse a generic lower bound for eigenfunctions on the torus.
Yeah, so my question is, are there nodal domains, let's say with very high eigenvalue, where you expect the curve to be quite fractal, or have high dimensions, roughly speaking? So it's sort of space filling or something like that.
So depending on what you mean by that, for each finite energy, they're all smooth.
Yes, I understand.
But as the energy grows, the aspects. If you want something very long of macroscopic order, no one knows. But it's a very interesting question of order bigger than some big constant over square root of lambda once. No one knows. So generic lower bound. Okay, part 2. Toral eigenfunction. Okay, so take what is the torus is just R2 divided by Z2. Everyone knows that. If we take a function of the following type, phi of x, e to the power e of mu x, so this is just e to 2 pi I mu of x. X is x1, x2 on the torus, and mu is any number, any tuple in Z2. Then this function phi obviously satisfies is very easy to check. Obviously is a function on the torus and obviously satisfies the Schrödinger equation. And what is the eigenvalue? Lambda equals to 4 pi squared mu squared, where mu is the Euclidean norm, where mu is in R2. Okay. Now denote this number as n. And if we happen to have two guys mu with the same Euclidean norm n, then we can sum them up or have any. Yeah, I'll explain that. So this function. So this function is complex valued. Yes.
Different question. So in a nodal component, can you have like a figure 8 or something?
No, not generically. Non-generically.
Yes. The answer is yes.
Yes, but non-generically.
The ones he's writing down cross each other.
But non-generically. But
The question is, can you have? The answer is yes.
yes. But the
There's actually a theorem that says that when crossings do occur, they occur in equiangular sectors. It's not completely arbitrary. But Igor was saying that if you, in his setting, you can perturb in the final dimensional eigenspace, then generically there would be no
yes.
level crossing.
Okay. So if we take any linear combinations of these guys with mu varying but having the same Euclidean norm, then we're still, by the fact that the eigenspace is a linear space, we're still lying inside the eigenspace. And therefore, I'm going to write down the general form now of some eigenfunction. Let's take n. It cannot be any arbitrary n, but it has to be a sum of two squares. Then Fn is a summation of A mu E mu x, where mu varies on a circle. So mu varies or is a lattice point lying on the circle of radius squared of n. And A mu are some complex constants. So this is the general form of a complex valued eigenfunction on the torus.
What if I give the torus a different aspect ratio, so I have some
Right.
irrational? Then I might have actually uniqueness, right?
So if it's rational, then sorry.
Yeah. So if it's, I want an irrational aspect ratio.
If it's irrational, then there is only a multiplicity 2.
Yeah. And then you say, does your work apply to that case?
Then you'll have to sum up guys with different energies. My work is not applicable in that case. If that's
Because you have to take the superposition.
you have to take superpositions with increasing multiplicity. Otherwise, any theory of random fields will not work, and we do count on that heavily. Any other questions?
But do you expect the same kind of results to happen? I mean, is there something?
No.
The domains are completely true. They're
Yeah.
just checkerboards.
Oh, they're just checkerboards.
Yes. But again, if you sum up,
No, they're not checkerboards because you have multiplicity 4 or something like that. So
But not much.
we
two
take
or something
them
like that.
Nothing very much interesting happens.
no, you can
So we don't,
you can understand them explicitly.
can't randomize.
Yeah.
No, I understand. But you presume that's an easy case to understand.
Yes.
I know sine x times sine y. This
Yes.
one I know.
No, even but if you
But
take
if you have a combination of 4 guys like that,
Okay.
then the nodal structure is no longer a checkerboard. I
um,
don't know what to say about it because
but you can, in my opinion, you can still. In my opinion, I think that's quite easy to get. I think it's depending on whether or not
Never mind. But I'm sorry.
whether or not the ratio is more than 1 or less than 1. You'll get either in one direction. Okay, so if we assume that A of minus mu equals to A mu complex conjugate, then this function is going to be So whatever is above is a general form of a real valued eigenfunction. And the summation here is, as I said, over lattice points lying on the circle of radius squared of n. Maybe there are a lot of them, maybe there are just 8 of them. But this is the summation. Hopefully there are a lot of them. And it is known, and I will quote the results, that the nodal structure of Fn has everything to do with the angular distribution of lattice points on the circle. And I will quote 3 results, one by Kuhlberg, Krishnapur, Kuhlberg, and myself in 1930. One by Nazarov and Sodin that I'm going to explain in a bit what exactly they did. In 12. And another by Kuhlberg and myself in 15. And I'm going to explain each one of them what is actually saying. Okay, so not in each one of them, only 2 relevant of them. But before I'm going to speak about these results that are relating, let me just say, since I already mentioned that there is a relation between the angular distribution and the nodal structure, let me say something about the number theoretic aspects. So facts. So first fact is that the size of the summation here, the number of terms, is precisely as the number of lattice points on the circle, which is precisely the number of ways to express the number n as sum of 2 squared. So dimension, which equals to R2 of n. This is notation, which is mu, so that mu squared equals to n. And on average, it grows like some constant times log square root of log n on average. So it grows, but only just. There are infinitely many, there is a sequence of infinitely many n, which namely the primes, so that there are just 8 points. But nevertheless, on average, it slowly grows. 2. Okay, so this number is growing. There are more and more points. The question is where there are on the circle. And the claim is that generically, for a generic sequence, which means that for a density 1 sequence out of all numbers representable as sum of 2 squares, these lattice points are equidistributed on the circle. What does it mean? So what we do is the following. We take this circle of radius squared of n. We project it, so and these are the lattice points. We project it to radius 1. And we look at the probability measure, which is induced by those atoms. So we take nu n is the summation of delta mu divided by square root of n. Mu has Euclidean length square root of n, so mu divided by square root of n has Euclidean length 1. So on the circle, mu squared equals to n. We divide them by the number of terms. This is a probability measure on the circle. And this converges to the Lebesgue measure, to the uniform measure on the circle. So this is a Lebesgue measure number divided by 2 pi. This is only generically. But in fact, there exists some other weak star partial limits to this sequence of probability measures. So, for example, we can construct a sequence of n, of energy levels, so that the corresponding new n converges to a measure supported on 4 antipodal points. This one, this one, this one, and this one. So, new n convergent to delta at plus minus I plus delta at plus minus 1 quarter. And this is called the sequence. But there are other measures. So these are two extreme, equidistributed, Ciruelo. We cannot have less than 4 points because of the symmetries of this problem. It is symmetric with respect to complex conjugation and rotation by pi over 2. But the minimum possible is attainable. But there are some intermediate measures, and there is a partial classification of the weak star partial limits by Kuhlberg and myself. Now, what Nazarov-Sodin did?
Before you do that, so is there a natural sequence in which, you know, the convergence is sort of how optimal to the uniform measure on the circle?
I don't think that there is a natural sequence. There exists a density 1 sequence, but
you can't identify a natural.
not that I'm aware of.
You want explicit?
Yeah.
Yeah. Then you just take integers which are products of any relevant prime. Optimal just means that you can identify the ends for which converge to the uniform measure. Is that the question?
Yeah, I'd like to know whether there are natural sequences for which you have very good control over the convergence.
Oh, the rate of convergence.
Yeah.
Not that I'm aware of. And the convergence is quite slow.
So it's slow, but it's explicit. It's not serious. It's like one of them.
So what Nazarov-Sodin did is the following idea. So they endowed the coefficients a mu with Gaussian measure, and they assumed that they are all Gaussian IID. And they considered what happens with the corresponding number of nodal domains or nodal components as a random variable. So they proved the following statement. But here there is so the tricky bit here is that in order to exhibit some asymptotics, they have to pass to some sequence that converges to some measure. And the asymptotic will be different for Ciruelo or for the uniform measure or anything in between. So what they did is the following. For every new probability measure on the circle, there exists a constant, which we call the Nazarov-Sodin constant of nu, so that if we have a sequence n with the corresponding nu n convergent to nu, then the expected number of nodal domains of Fn, which is a random variable, is Cns of nu plus O of 1 times n. And this constant is greater or equal than 0, of course, because we count a positive or non-negative quantity. And usually, it's non-negative. Usually, it's positive. Yes, a non-negative number is always non-negative. But in fact, usually, and I'm not going to explicitly say way when, but I'm going to say in this situation, sufficient and necessary condition when it's positive or when it vanishes. So one small remark is that even though here we use the Nazarov-Sodin constant only for a weak partial limit of the atomic probability measures, it makes sense to define it for any probability measure on the circle. So facts.
They have to assume that the ANs are independent or anything like that?
Yes. Oh, yeah.
Gaussian?
Gaussian.
Okay, Gaussian independent?
Yes. In fact, I should. Yes. So I forgot to say it, and that's the most crucial thing. Assume that A mu are Gaussian IID safe to A minus mu equals to A mu bar. And you can write it with cosines and sines explicitly in a real form. And then, otherwise, this doesn't make any sense. But with this, this is true. And in fact, this convergence is not just convergence by expectation, but they have also convergence in mean. In mean or in L1. The expectation of the absolute value of the difference is small o of n. Now, facts. So what about this Nazarov-Sodin constant? So as nu varies along all partial limits, the corresponding constant attains an interval of the form 0 C naught along weak star partial limits of nu n. Cns of nu attains an interval 0 C naught, where C naught is some positive number. And conjecturally, it equals to the Nazarov-Sodin constant uniquely of the uniform measure. No one knows the answer to that question. And Cns of nu equals to 0 if and only if nu equals to either this atomic measure supporting 4 points or the same one tilted by pi over 4. So these are the only measures that satisfy the invariance and are also supported on 4 points. So this result is due to Kuhlberg and Wigman in 15. And in fact, attains continuously. Where the topology on probability measures is the weak star topology on probability measures. Now, what Bourgain did is he proved the only deterministic result using a brilliant de-randomization idea. I think it's so. First of all, he assumed that all the constants are equal to 1. Take Fn naught is the summation E mu x. So A mu are all equal to 1. And he made two extra assumptions. First assumption is that the lattice points become equidistributed. So lattice points becoming equidistributed, so nu n converges to d theta over 2 pi. And the second assumption is that there are few spectral correlations. What is a spectral correlation? A spectral correlation is a tuple mu1 mu b, so that sigma mu I goes from 1 to b equals to 0. So for example, mu1 plus mu6 equals to 0 when all the mu I are lying on the same circle. And he assumed that there are very few of them. For example, we can take mu1 minus mu1, mu2 minus mu2, mu3 minus mu3. This is basically what this assumption says is that there are very few non-diagonal, non-trivial spectral correlations. I'm not going to say anything further just because I don't have time. Yes, but here we're only interested in the not degenerate case. Okay, so these are the assumptions, and his conclusion is then the number of nodal domains of Fn naught, which is a deterministic sequence, is asymptotic to CNS of the uniform measure times.
You might point out that instead of Nazarov showed that almost every choice has this property, also not just the expectation.
Yes, by probability, but this is not a deterministic.
This is deterministic, but the theorem is much stronger. It's not about the ensemble average, but about each typical guy has.
Yes, yes.
He's now de-randomizing, as you said, showing explicit averages.
So he showed an explicit example where this is satisfied. Okay. Now his argument is that if instead of averaging over coefficients, we average over the whole torus, then this is becoming Gaussian. I actually plan to say a few words, but if I will, then I will not have time to present our own results. So unfortunately, so now, so maybe next time I should prepare slides. I don't know. So what we did, our goal was, just to remind you, I promised some lower bounds. And it's going to be a corollary from the result I'm going to present, a generic lower bound. Now, we are going to relax the condition of equidistribution. That is the first assumption of Bourgain. And we're also going to relax the condition of A mu being equal to 1. These are no longer equal to 1. Now, so relax equidistribution and a mu equal to 1. We may assume, with no loss of generality, that sigma a mu squared equals to 1 just by multiplying or dividing by a constant. Now, if we indeed assume it, then we expect most of the numbers a mu to be of the size 1 over square root of the number of the terms. And we're going to assume a growth condition, so we don't want to deviate from this bound too much. So let G be slowly growing. So for example, power of logarithm. And assume that the maximum satisfies that m is growing slower than g of R2 of n divided by R2 of n. So this is a generic assumption on the coefficients. One more thing. So where did this Nazarov-Sodin constant of the equidistributed measure come from? It came up from the assumption that the measure becomes equidistributed. But here we can play a lot with the coefficients. And it's not fair to compare it to the equidistributed case. So we have to introduce a different measure. And the correct measure turned out to be nu n a, which is sigma a mu squared delta mu over square root of n. So this is a probability measure on the circle because of the assumption that the summation of this guy squared equals to 1. So now I'm in a position to formulate the result, or the first result. Okay, so suppose that we have a sequence n, so that we have nu n sequence of n and a sequence of sequences of coefficients a mu n. So for each n in this sequence, we have a sequence of coefficients. If we go to another n, we have a new sequence of coefficients, and each of the sequences is finite. So that nu n a convergent to some measure nu. We again assume the assumption of Bourgain about the few spectral correlation. And then n of f n is c and s of the limiting measure times plus O of 1 times n. So this is an asymptotic result. I take one sequence of the coefficients so that the corresponding probability measures converge to a limit probability measure. And the corresponding number of nodal domains is asymptotic to n times the limit constant. And the limit constant corresponds to the limiting measure by the Nazarov-Sodin. And by the way, that implies that we could not possibly just straightforward generalize Bourgain's result because it's wrong with the same constant. We have to, and we know that this constant is varying, generally varying with the limit probability measure. Now, I promised you a lower bound. So seemingly, if this number, if we take a family of coefficients A, so that this number will be fluctuating by bounded away from 0, then that will already yield a lower bound. But there is a problem here. What's the problem? Suppose I take two different sequences of A that satisfy all the assumptions, but converge to different probability measures. Even though they are positive, for given an epsilon, to get sufficiently far with n, we have sufficiently far will depend on the sequence A. And I would like to formulate a uniform result. And a uniform result will certainly yield a lower bound. But there's a problem. If I want to formulate a uniform result with respect to A mu that satisfy this growth condition, then they obviously converge to different probability measures. And there's no limiting measure. So therefore, what Nazarov-Sodin constant are we going to use in the result? And the answer to that is that we're going to use the Nazarov-Sodin constant not of the limiting measure, but of the finite measure. So now theorem 2. And I have minus 1 minute, therefore I'm going to be very fast. So again, we assume the few spectral correlation assumption. Okay. So theorem 2, which is going to be uniform result. Let me use this inequality. So for every, let me format it. For every epsilon, there exists an n naught, which depends on epsilon and g, so that if n greater than n naught, that implies that for every A satisfying the growth condition, n on f n A minus the Nazarov-Sodin constant of. So this is the crucial bit that we are not using the limiting Nazarov-Sodin constant, but the finite one divided by n smaller than epsilon. Now, so this theorem, so because we have this Nazarov-Sodin, finite Nazarov-Sodin constant, and not the limiting one, seemingly it does not imply theorem 1. But in fact, it does imply, because the continuity of the Nazarov-Sodin constant in the weak topology that I formulated a few minutes ago. And as I said, from this result, if we have a collection of coefficients A, so that the corresponding Nazarov-Sodin constant is bounded away from 0, that already gives us the lower bound of the correct order of magnitude for the number of nodal domains. So lower bound, generic Fn. So I think that. Say again?
Much stronger than generic, just satisfying these inequalities, right?
It satisfies these inequalities. Explicit generic, deterministic generic.
Just if f is a Fourier series, I mean, the theorem should be just stated. Suppose I have a Fourier series, summation a mu cos 2 pi mu x in dimension 2. The a satisfies that condition, then the number of nodal domains is close to the Sodin Nazarov constant.
Yes.
If you have this other thing about few correlations, which has to do just with the number n.
Yes, and also you have to take care that Nazarov-Sodin constant is bound away from 0. For example, you have to be far away or sufficiently far away, epsilon far away from the Cirella measure. If all your coefficients.
Where did you put that then?
So in that case, the Nazarov-Sodin constant will just vanish.
Be close to whatever it's supposed to be close to.
Yeah.
Okay.
Yes, but then you don't have. Then you don't have a lower bound, and there.
The question is, you just have a
Yes.
count of the number of nodal.
Yes, and also it shows that in fact you cannot possibly prove a lower bound if you have any sequence, whether it's CLL or not, with coefficients being concentrated in one of those 4 points. Then there doesn't exist a lower bound because there is a small o of n nodal domains, which was not known before that actually. And I think that I'm going to stop now. Maybe next time I'm going to use slides. I'm not sure.